All right, so one of the things that's going to pop up for us a few times is what's called this. Well, let me just get, maybe I should start it a little more, uh, maybe a little more from the beginning. So, I can't get my camera where I want it to be. So, here's something that we're going to be interested in. So if you pay attention to the language I'm using here, I'm saying that this is an important result about work. So just a little bit of a background of what happens here. One of the things that we do in like math and we do it in physics, and I guess in science in general, but it's more associated with math and physics stuff, is we have these ideas of, okay, we create a set of axioms or a set of definitions, something that we all agree on is, here's the rules we're going to play by. You know, in physics, we have these theories. For example, we can think of Newton's laws as the rules, you know, the quote unquote rules. We know that most things that we observe in the universe adhere to the laws of Newton. And then what we can do is we can hypothesize other things. We can say, oh, well, maybe if these conditions are met, this will happen. Or maybe if these condition along with that condition is met, then this will happen. And oftentimes what we do is when we can derive something from a set of axioms, or if we can derive something from a set of definitions through logic, we give it a name. And usually in math and physics, we say things like a proposition or a theorem. Now, these are words maybe you've heard undoubtedly when you were a young kid in high school or middle school. You took on a geometry class or learned about geometry. And that's one of the places where the school systems think they're going to teach you about logic and deductive reasoning. And then you do these little things which we call proofs. And you might remember having to memorize these angles like side angle side theorem and similar triangle stuff. If you go in your brain time machine, you might remember that. And so that kind of stuff happens at the highest level of physics and math right now. And one of the important quote unquote theorems that we use in this class is what's called the work energy theorem. And so we can write it down in English and we can write it down in symbols. And one of the things that we do is we've used it, and we'll use it for some problems. And if you did all the problems on homework 3 already, you've actually used it. So what does the work energy theorem say? So it says that total work done is equal to the change in what we call kinetic energy. So in symbols, we usually write it with W with a subscript total. And then we use, anytime we want to discuss change, we use this triangle. So for those of you who've seen it in the book and quite maybe just wrote it down or saw it elsewhere and just wrote it down. This is the Greek letter delta. So in math and physics, engineering and stuff like that, we use this letter to represent change. So if you look at, let me pull it up because I don't remember what number it is. So if you look at problem 4 on practice set 3, homework 3, I give you this formula, W equals P times delta V. And this turns out to be a useful formula for us if we're trying to understand the basic things of, for instance, something that would be important in your line of work, and that is, say we have gases and we're expanding and contracting, and we want to know how much work is done on such a thing. So what we'd like to know is how does this formula come about? Where does it arrive from? So before we go any further, does anybody have any question about this? And by the way, I guess we should say it anyhow. Kinetic energy is 1/2 times mass times velocity squared. So one of the things you need to understand is and maybe I should say this as well because it might not be clear. Oftentimes we as students and learners, we forget that there's a difference between a definition and a result about something. So for example, what is work? Work, by definition, is force times distance. Now that can mean very simple thing, or that can mean, excuse me, a very complicated thing. Because if the force that we're acting on is not in the same direction as, I mean, I don't want to get too into detail with it, but direction matters is a simpler way of saying it. So, for example, typically in the definition of work, you find what's called, you get an angle involved. Now, this often can simplify to just force times distance. If, and this is an important fact, if the displacement and the force are in the same direction. So I'm not quite sure if that makes sense to you at this point, but a good exercise to think about is imagine you had a cardboard box and you wanted to push it across the room. That would have one amount of work. Whereas if you had a box and you wanted to push it up a ramp, that would require something different. So think about how you're pushing the box versus where it's going. And you can think about how two formulas might be different. Now, again, everything on this page right here, and this should be noted, is these are definitions. And what happens is oftentimes definitions are hard to work with. And so fortunately, when you have a result like on the previous page, you have this, what we call the work energy theorem. What it often does is it allows us to relate two quantities without having to go back to some more complicated definition. Actually, instead of my little box exercise, think about something that might be more relevant to what you've done. Maybe you're pushing a patient from one room to the next. Well, that process requires some amount of work. Whereas if you had a patient on a hospital bed and you had to push it up a hill, that would be different versus even pushing it down a hill. All right, does anybody have a comment or a question about this?
Nope.
Yeah.
No.
No? Okay. All right then. How about, okay, I know another question I wanted to, is everybody okay with, actually, before we do that, let's do an example that's similar and make sure that you got problem 4 correct on the homework. So let's do that. So suppose we have some volume of gas, and it could be any volume. It doesn't matter. It can be a ball, or it can be, I mean, you can imagine any volume of gas you want. But what I would always ask you to do is envision sort of models. I like to call them a model. For example, in a little while, we're not today, but when we start talking about fluids, in the real world, we're interested in fluids in lots of different ways. And we're interested in the blood that flows through your body. We might be interested in how the water that goes down the river wears away at the riverbed. I mean, we can think about fluids moving in many different ideas, but if we want to study them using the laws of, say, physics in the language of mathematics, then we have to use simplified models. So one of the best ways to think about how we might study your blood in a vein is to simplify that model to maybe water moving through a hose. Or if you want to, quote unquote, model the process of breathing, air and oxygen coming into your lungs and then going back out. One way we might model that is we might think about a cylindrical container. that brings in air and then releases air. So don't forget, when we're trying to solve problems, we have to simplify the real world experience to some sort of what we say model that we can use the language of physics and the language of algebra or calculus, if it may, to solve these problems. So if I write something like a volume of gas, you can imagine, for example, you have some cylindrical container and there's gas in it. So let's look at one of these sort of what we call baby textbook examples. So a volume of gas increases from 1 to 4 liters against a constant pressure of, let's say, 500 pascals. So we want to determine the work done. This is a very standard, what we would call textbook example of using these ideas. Now, in the problem on the homework, I gave you the formula. I said work equals P times change of V. But suppose I didn't give you that formula. Suppose this was the problem and you had to solve it without the hint. How would we arrive at this formula?
The word work is in the formula.
Right, I get that. But how would you know that work is equal to P times change of V? So I guess what I'm trying to get at is if someone doesn't give you the result, how would you obtain it? Now, I guess if you wanted, you could solve this straightforward, perhaps. You'd have to be a little, maybe take a little bit of liberties with your algebra. I mean, if you started with the definition of work, you might say, okay, how could I get this change of V involved, and how do I get pressure involved? So let's kind of investigate that, if we will. So on the homework, I gave the useful equation. But the question that I have for us, and I want us to think about at least, is where does it come from? So, I mean, earlier I said an important thing. I said this work energy theorem. We talked about kinetic energy, and we gave you this definition of work, which hopefully you've already read, and said, okay, yeah, work is force times distance. So if we start with what we call a model and the definition of work, what we can do is we can use some algebra to, what I say, derive the equation work equals pressure times change in volume. So here's the way I would tell you to think about it. So a basic model is a cylinder. So let's assume we have some cylinder. We're going to use this model for lots of things. And by the way, why do we want basic models? Why would a cylinder be a model that we think is basic and useful? Well, we want models that have simple geometry. And the cylinder has simple geometry. It has symmetric aspects to it. Its size and its cross sections are very familiar shapes. If it's not hard to get or at least memorize or understand the geometric properties of a cylinder. And since, by the way, you might keep saying, why do geometric properties matter? Well, think about things like pressure. Pressure, by definition, involves geometry. It involves the size of an object. So also, if we're talking about expanding or contracting gases in sizes, right there, that's talking size, geometry. So we want to keep this in the back of our mind. Do we have simple models? So if we have a cylinder, we can think about its geometric properties. For example, it has cross sections are circles. So, you know, the cross section are circles with some area. And we know the area formula of a circle is pi r squared. Now, the one, you know, sort of devil's advocate or question that you might say is, you're going to say, okay, well, we know in real life that not everything a lung is in a cylinder or something else. Yeah, you're right. This is a simple model, but the good news is, even if we don't use a simple model, you can do the same reasoning we're about to do. The only difference is, if you don't have a simple model like a cylinder, then you would have to replace that word algebra with a more fancy word, calculus. And since we're not assuming that you know calculus, we're not going to do the more general derivation. We're going to stick to a simple model that has a very simple algebraic derivation. But what we're going to do can be generalized. And if you use more fancy math, you can derive the formula in any scenario. Okay, so does anybody have a comment or a question about this? All right. So here we go. So if we hold to take our cylinder and draw it again. Well, actually, let's assume that this cylinder has a specific length. So let's assume the distance from here to here is, say, I don't know, let's just call it h for the heck of it now. So imagine that I have some volume of gas, and that gas is in this bottom portion up to this red. So I'm trying to shade that in. So this could be some substance. I don't care what it is. Maybe it's gas. Maybe it's fluid. So the volume of whatever that substance is, the volume is pi r squared, its area times how the height of it, which in this case, since it's a simple cylinder, is just h. Okay, so here's what we want to think about now. What we'd like to do is we would like to imagine now we have some substance, maybe in this particular example, it's gas. And we would like to imagine it takes up this much space. And then we'd like to imagine now it takes up a new amount of space. So for example, on problem 4, we go from 3 liters to say 5 liters. In this example that we're currently working on the class, I think I said from 1 to 4. So we need to imagine that this gas is, the volume is increasing. So one way to imagine what happens is what happens if this volume increases. So and I'm being very careful with my words, and I'm putting, we're not being very technical. We're using these words in, like, I guess, the colloquial way. What do you think increases means in this scenario, that kind of stuff. But once again, suppose we go from, get a picture here. Here's my cylinder. What color did I use? I used pink, I think. We'll stick in pink. Pink's a nice color. So if so if this is my, say, 1 liter, and then it grows to I want to keep these consistent. Sorry about that. I need an art degree. So imagine this is our cylinder. And suppose now it increases to 4 liters. So one way to sort of analyze this is to think about the difference. Think about that cylinder that we just obtained. Because if you sort of line these things up together, we can think of this piece right here, this new piece. We could think about that's what we gained. And we can study this piece. Oftentimes you'll find in books they'll ask you, or not ask you, but they'll give you what, maybe if you have any familiar with like how an engine works or how a piston works, to imagine this is like a piston. I don't know if any of you are familiar with that, but I do know books tend to use that sort of description. I like to think, and I forget the name of them, you're probably familiar with them. What's one of the machine, not a machine, it's like a device that if a patient's in the hospital and they're having issues breathing, one of the things that they ask you to do is they ask you to breathe into that machine, and they see how strong your lungs are. There's a name for that. It escapes me right now, but I'm sure you're all familiar with it. You can imagine that thing, like sort of the little accordion thing going up and down. That might be a good way to think about this. Okay, so does anybody have a comment or a question? For those of you wondering why I'm kind of spending time on this, don't forget, I mean, part of the things that we would prefer that you learn in a class like this is that you become a better problem solver. So what that entails and what that means to me and to other people is that you understand how to set up and work your way through a problem. A lot of times, especially when we're in class, we get sort of in love with this idea of just plugging things in the formulas. And that's okay. That's not wrong for you to plug numbers into a formula. But if you do that too much, what you're losing is you're losing any understanding of what's happening, and you're losing any understanding of the reasoning. When you just plug things in the formulas, you're more or less just becoming a cheap, slow computer that's likely to be wrong more than a computer is. So what we want you to do is we want you to understand how a problem can be set up, how you might attack it from different angles, and then how you obtain a solution. And that's my opinion on the best, for you to get, I don't know how to say this without coming off like a weirdo, but I mean, look, I'm not a fool. We know why most of you are here. Most of you aren't taking this class because you're excited to learn about physics, right? This is an ends, means to an ends. You guys want to get a certain degree. You want a sheet of paper. You want to make money. I get all that. But part of when we're taking classes is we want to become better at something. We want to, learn new skills or hone certain skills. And one of the things that I think is important is that you become a better problem solver. So that's sort of why I'm spending time on this problem, whereas you might just say, well, isn't there just a formula in the book, and can't we just plug in numbers in? And yeah, sure, that's one way that you can think about this, but I don't know that your brain gains anything if that's the way you think about it. Okay, so with that being said, what I think is being one way that can help you think about this problem is that new part. There is a distance that this went from here to here. So what I want to do is I want to call it D. And I want to analyze the volume of that new part. So before we do this, let's note an important fact. I don't know that this was ever taught to you. So we're trying to get an idea of a general sort of situation by using this cylinder. And I said earlier that this argument can be verified not just with cylinders, but with other more general geometric objects. And one of the facts that it's not a fact, it's more of a definition, is the following. Volume, by definition, is cross-sectional area we're being very generic here, but I think you'll find that I'm not lying. So it's cross-sectional area. I guess I should spell area correct. Times height. So I'll put those things in. So that's what you get up here. You get with the cylinder, the cross-sectional area is pi r squared. So what we'd like to think about is that is area times height, which we'll call h. So what I'd like to do now is I would like to think about this picture with the top cylinder with the pink substance, and then I want you to imagine how it grows to the bottom scenario with the pink substance. And we want to think about the quote unquote end of the pink, how it moves. Well, where does it go? It goes a distance of d, because I labeled it that way. I said I want to imagine how I want to analyze this quote unquote new part when the gas expands, and I want to analyze the geometry of it, because I know the geometry is important to things such as work, and the problem asked me to study work. Okay, so let's sort of think about that. The piece I'm interested in is this now. I'm interested in this cylinder. It has a height of d, and then it has a cross-sectional area, which I'll just call A for the heck of it. So we know, what's the volume of this? The volume of this is its cross-sectional area times d. Now, using basic algebra, we can rewrite this, divide both sides by A, and you get d equals volume over area. Now, there's two reasons that I want to rewrite this equation. The first is that I know by definition that work involves this d. It involves some distance. But also, the reason I'm interested in it is also I know that if I have a ratio, sort of, how do I say this without, in the back of my mind, I guess, maybe because of my experience. My experience tells me that when I have ratios of areas, and when I say ratios, I have a fraction. And on the numerator, I have volume, and on the denominator, I have area. And one of the things I know is that looks similar. It's not exactly it, but it looks similar to me to what the definition of pressure is. Now, you might say, well, why are you even thinking about pressure? Well, I'm thinking about pressure because in the statement of the problem, I'm told there's some pressure. So in the back of my mind, I'm thinking two things here. I'm thinking, how do I get pressure involved? And how do I get the definition of work involved? Now, of course, is amateurs or people in your shoes, you would probably not be thinking this. But what I'm thinking is, what are the givens in my problem? What do I see in my experiment or whatever I'm doing? What do I see in a patient? Oh, I see that this volume of gas is increasing from blah to the next. And then I also know that there is a pressure involved. So what I have to do then, what my job is the physics student, is to figure out how do I get the equations that give me information about those quantities, how do I get them involved so that I can solve the problem. So, what this reminds me of is, you know, is how students, one of the complaints I get all the time from, our undergrad students is they take a lot of math and then they get to physics and they hate physics because they say it's hard. And part of the reason, well, I guess everything's relative, whether it's easy or hard, but part of the things that makes physics hard, and I'm saying that from a student perspective, not from any other perspective, but physics is really like the thing that you dreaded your whole life in school. What did most people hate in math class when you were in school? You hated the word problems, you hated the story problems or the applied problems or word problems, whatever you want to call them. And that's really what physics is. Physics is like, in a lot of ways, it's just lots and lots of word problems. And that's difficult because one of the hardest things for us as students and learners is to take English sentences with a little bit of numbers in them or a scenario in them and formulate that in the language of math that allows us to determine a solution. That's a very difficult thing. You look at this homework, some of these things are easy. Like, I mean, some of these problems are literally just plugging numbers in and chugging, or some of these are just converting units. But other ones like this, which isn't too bad because I gave you the formula, but if I didn't give you that formula to use, it would be a very difficult problem. Okay, does anybody have a comment or question right now? I don't know if you do or don't. Feel free to say anything. I don't know. Maybe you had a great weekend. Maybe you didn't. I don't. Okay. So back to this situation. Okay, now here we go. So here's my work. So by definition, work equals force times distance. Now let's think about where I'm getting this from. That's the definition of work. Now, what I want you to think about, as I said, that what you need to envision is you need to envision this pink substance, which I guess we can think of as a gas. And think about the roof of this substance moving right. It's moving right a distance of d. And it's moving right, and it's got a battle going on because there's a pressure going against it. And this pressure is held constant at some fixed pressure, which I gave, I forget what it was now, 500 pascals maybe. I have to go back and look. So what I need to imagine is that there is work being done, moving that substance, expanding it. And what I need to think about is okay, what's it against? Well, you can imagine the pressure is against the other end, so it's in the same line, so we don't need any angles. So that's why the cosine piece is not there. All we need to know is that the gas wants to expand this way and the pressure is fighting against it. So they're in the same sort of direction. Now, that is the definition of work. The next thing I note is by what I have at the top of the page, I can replace D with this volume over area. So what I'm doing now is I'm replacing that distance, D, I'm replacing it with the volume divided by the area. And now what I'm going to use is I'm going to use a very basic fact that you would have learned in 5th grade, but it's one fact that really bothers us as students. And just to beat the dead horse, if I had, for example, 3 times 7 over 2, in 5th grade, you would have learned how to handle this. You know that this is 21 over 2, because 3 times 7 is 21. You would have also learned that 3 over 2 times 7 is the same thing, is 21 over 2. So in general, a basic fact about numbers is if you have a number A, I don't want to use, so let's use little a, and then you're multiplying it by the fraction A, B over C, this is the same thing as AB over C, and it's the same thing as A over C times B. That's 3 ways to write the same number. And so what I'm suggesting is I can use this basic fact about numbers, about arithmetic, and I can rewrite this formula as F over A times V. But what is F over A? F over A, by definition, is just pressure. So what you get is you get this very sweet and simple formula. Work equals pressure times volume. Now, we're not done yet. First off, this doesn't even look like, it's not exactly the equation I gave you for the problem, and we're going to explain that in a second. But what we did is we did reason that the work done is equal to the pressure times the volume. So here's the problem about real life, and here's the problem in general. We didn't make any assumptions about anything to derive this equation. We didn't make any assumptions about the pressure, yet at least, and we didn't make any assumptions about the volume. All we did is we basically said, let's analyze that piece. So let me go back a couple slides. I wanted to understand this new part, as I called it. So I did it in the most basic sense. I said, let's call this distance D, and then let's play around with some algebra. And then when we play around with algebra, we get this equation. But it's possible that both pressure and volume are going to vary. So what we can say finally is we make the following and final assumption. So if we assume pressure is held constant and volume changes, here's what we obtain. We obtain that work equals pressure times whatever that change is. So this is a very, I shouldn't say very simple. This is a sketch of a simplified version of a much more sophisticated argument. Here we assumed we had this cylinder, and using this cylinder, we can reason that this formula makes sense. But as I said earlier, this formula can be derived in full generality. It just requires a higher level of mathematics, higher level of reasoning. And then once you have the formula, it's real easy to use. As you guys know, you're just plugging numbers in and multiplying. Now, one of the concerns you might have, or, I don't say concerns, but you might be thinking right now, well, I would have never have thought of the problem this way. I'm just plugging numbers into the formula. And again, let me reiterate, no one would expect you to derive this formula on your own. That's why I gave it to you. What I would hope you do, and I'm not going to force you to do it, and I'll never know if you did it or not. What I would encourage you to do is to try to work through this reasoning and think about if you understand where it comes from, because those ideas can be used to derive other things later on in this course and other aspects. Think about the thought process, the deductive reasoning, not necessarily the specific letters in this problem, but the process of reasoning. And this is not easy to do. It's usually something students don't like to do. And so I'm not going to blame you if you don't, but I would encourage that you try to do it. Okay, great. All right, now let's solve this problem. Now that we did all the difficult work, now it just becomes arithmetic. So we'll change colors. Does anybody have a comment or a question before we do this? So let's go back to the problem. What were we given? I got to slide back like a bunch of slides because I don't remember what numbers I gave us. So 1 to 4 against 500 pascals. Okay. So the pressure here was 500 pascals. And then the volume it went from 1 to 4, so that would be 3, right? 3 liters if I go from 1 to 4. All right, so one thing we should do is I'm always interested in a class like this. I don't know how familiar you guys are with standard, like SI units and all that stuff, or what is required of you in other classes. My train of thought is to always use the SI units. So that's sort of what I'm going to go by. Use the standard ones. And so that means you got to do some converting before you do anything else. For example, what are the standard units? We're computing work, right? So this is the way I would tell you to think about it. So what is the standard unit for work? Well, the standard unit for work is the joules. And what is a joule? Well, if you go and look up, these are things, again, I don't know. Some people get annoyed with me, but I think you should know, at least have a readily good idea of what work is. And what is its SI unit? It's joule. And what is a joule? A joule is a kilogram meter squared per second squared. So that means we need to get these guys into the proper, excuse me, into the proper place. So what is, for example, what is a Pascal? Do you know the units of Pascals? Or excuse me, Pascal is the unit. Oh my God. I think I did have a stroke. So it's a wild world we live in. So can we write these things out? And I think this is good sort of exercise to do. What is a Pascal? Pascal is, think of it as a Newton per meter squared if you wanted. But it's a kilogram over meters per second squared. That's one, at least that's the one I remember. And then, of course, you can't have liters is not the SI unit either. So what do you have to do? You have to convert liters to meters. Now, one way to do that is go to the Google machine or a calculator. However you want to do it. So we can't write, remember a liter is a three-dimensional thing, and so a meter's one-dimensional thing. So what do we have? Well, this would be meters cubed. So one way to think about that is this is 3 times 10 to the negative 3 meters cubed. Or if you want to use decimals, you move your decimal over 3 places. Does anybody have a question about this, by the way? Again, it's really hard to tell. Obviously, we're not in the same room. So it's hard to get a gauge on this. Sometimes students are real good with units. Sometimes you guys are terrible at it. The good news is in 2020, almost every conversion you need can be found on your phone in a second just by typing it into Google. Questions, comments? Okay, so all we have to do is plug and chug now. So let's do it right here. Well, we'll do it on the next page. And by the way, if you just want to do all the arithmetic on a calculator, that's fine. I've told you that before. So work, which is pressure times change in volume, is 500. Which one did I use? Now I forget. Kilograms over meters per second squared. And then that's times the change in volume, which is 3 times 10 to the negative 3. So maybe we'll just write it to so it's not so ugly looking. Let's write it like this. .003 meters cubed. Is that what I had? Well, yeah. All right, and then you could just do the arithmetic. 500 times 0.003. So you're left with 1.5, and then what happens here? This is where, you know, Sora, I said this the very first day of class. I think I mentioned it the second time we talked too. What you need to do is, in my opinion, is write out all your units, because that allows you to line things up. If I do sort of the old-fashioned, you know, this meter cancels with one of these and you're left with two. I know this seems like grade schoolish, but I think it's important when you're doing this stuff. It helps you not mess up. And then you're left with kilograms meters squared over seconds squared. And if you go back, that is officially what is by definition a joule. And that's it. That's the work done. Fun times. Does anybody have a question about this? Of course, you could have used different units. I'm just saying this is how I would have done it. Maybe you use Pascal times meter cubed. That's the definition of a joule as well. Or definition, that's one description of a joule. Does anybody have a question? Comments, concerns? All right, any other questions about problems on this homework? Couple things that I can say while you're pondering, if you want to ask anything, is one of the things that I found students are I don't want to say confused about, but this idea of kinetic energy is the same for all sort of systems. It's always 1/2 mv squared, but potential energy does not have a standard formula. Potential energy, we do have standard formulas for certain scenarios, like we have for falling objects. We understand how gravity is a potential and interplays with that. For springs, we have this thing called Hooke's law, which describes the potential energy. But in general, potential energy, there is not some simple formula for us to use. So, for example, if you look at problem, what is it? Problem 8 on the homework. The first part of problem 8 is asking you to determine the potential energy of a falling ball. Now, you might say, well, what the hell does this have anything to do with the kind of stuff that you need to learn? Well, maybe this particular problem doesn't, but it's a good idea to help you understand why potential energy is sort of easy to sort of unify the way kinetic energy is. As you would imagine, what's going to cause more of, you know, a headache? If I have a bowling ball and I hold it 3 feet above the floor and drop it, you would imagine it might not be as loud or as damage causing as if I held that same ball 30 feet above the floor and dropped it. So the purpose of me assigning problem 8 is it's an example, hopefully to help understand what potential energy really is by comparing and contrasting with what kinetic energy is. So anyhow, I hope you sort of think of it that way. And the other sort of topic that, and I guess I'll find this out when I grade everything, it's interesting that many of us use words in the English language all the time, even though we're not quite sure what they mean. We just think we have some understanding of what they mean. And a great example of that is things like heat and temperature. And the other example, which is very much related, is this idea, if I have a room full of students and I say, whoever gives me the correct answer without looking it up, I'll give $1,000. And then I give you this question. I say, define boiling point. 99% of you will say the temperature at which water boils, which always makes me laugh, because how the hell can you define something and use the word you're trying to define in the definition? So things like specific heat, things like temperature, and the definition of heat and temperature. These are things that you should really work at trying to make sure you understand. That is my sort of challenge to you. Can you do problems, and can you explain? You notice one of the problems I ask you to do is I say, describe the difference between heat and temperature. Describe the difference between work and energy. Can you do these things? Can you describe them? Because the best way to truly understand if you get something, if you understand it, is how well do you explain it to someone else. So I hope you take these problems seriously. You don't just kind of write them off. Does anybody have a question about any of these other problems? Going once? Has anybody emailed me and I didn't respond? Because if that's the case, I feel bad. I don't think anybody in this class did, but I just want to make sure I'm not ignoring anybody. All right, good. Actually, maybe someone did email me and I didn't respond. I feel like a bad parent now. Okay, any questions, comments about this?
When will we expect to see grades?
Yeah, that's a good question. Soon. You know what? I'm going to try to start that today. Here's what I'm going to tell you. It's funny. We were actually talking about this. I was golfing on Friday with some people, and we were saying, look, if you turn the homework in and it's remotely done well, you're going to have, you guys should all, as long as the homework's submitted, you should be having, 8s, 9s, and 10s on this, which means you shouldn't be, every one of you who's submitting homework should, I'm assuming, will be above average of, and I'll yell if it's not. I just started grading my other class the other day, so you guys will I'll probably start today, and it'll be up there today or tomorrow. But I don't think you guys are going to have concerns about your homework grades usually. What typically happens, it depends, because 2 years ago in this class, was it 2 years ago? Maybe it's 3 years ago. The students struggled mightily on the first test, and then I kind of switched up how I did things, and then you guys, that class did great going forward. Usually I get a good barometer, pun intended, on how you guys are going to do once I look at the first couple of homeworks. And so I wouldn't be concerned right now if I were you guys about your grades. As long as you're submitting homework, you should be fine. And as long as the homework's done to a decent level. But I hope to start having the grades get updated on Canvas, maybe by tonight, but tomorrow for sure. All right. And here's one way to get me to bypass the other classes and go to you guys first is just blow up my email. Say, hey, when are you going to update grades? I won't be mad. It just kind of gives me like, hey, they're concerned. So if you really want something updated, all you got to do is ask, and then I'll get to it. Make sense? And you don't have to feel guilty about it. Any other questions? And we're going to talk more. So what I'd like to do is on Thursday, we're going to talk about fluids. That's kind of like one of our first, it's one of the big topics that we spend a fair amount of time on. So we're going to spend a lot of time on that on Thursday. But before we do that, I hope to kind of give you guys like, here's my assessment of the first 3 assignments. Here's how I think we're going. Do we need to go back and hit some topics, or can we move forward? So that's kind of my, because typically, again, if I'm using the past is my barometer, which is not always the best, but it usually works. What I found is the first 3 assignments in this class usually go pretty swimmingly. You guys are okay with these because we're not really going in deep on these topics. But once we hit fluids and gases, which are also coincidentally typically more important for the kind of stuff you'll be asked to do on exams and boards and all that, we'll go a little more in depth and we spend a little more time. So I think things will be a little more clear Thursday. All right. Any other questions, comments, concerns? All right. Well, listen, if you guys don't have any questions, what I'm going to do is I'm going to ask you to go over these notes again. I would ask you to think about that derivation, and if there's questions or comments about it, maybe, try to dig deeper into it. And then I'm going to post problems from fluids sometime this afternoon, and then we'll talk about that stuff on Thursday. All right. So if you guys don't have any questions, I say I'll talk to you then. And then I'll hold on for a few minutes in case someone wants to ask something. Otherwise, take care, study hard, and see you soon.